All right. Good evening, all. It's the evening of Wednesday, January the 5th. Going to get back to my normal curriculum here. It looks kind of blurry. Is it blurry to you? It is. I guess it's okay. Fine. We'll say it's fine. Uh, Climate change, global heating. There's been a lot of interesting weather lately, and that's not good news at all. It has been really damaging. We've had several what I call billion-dollar weekends where events during a particular week are sufficiently cataclysmic to have a price tag of about $1 billion. So I thought I'd come on here and give some context to all that and use it as a sort of a learning opportunity of how badly in trouble we really are. We're in big trouble, folks. We are in over our heads. All right, we do not have a handle on this. Not looking good. And it's early days in the global heating debacle, the predicament we're in. So I'm going to cover some ground here. I'm not going to spend a lot of time explaining some of this stuff. So I hope you can kind of piece it together. The first thing I want to do is make a distinction between global heating and climate change. I say these things a lot, and I really need to be very clear on what I'm talking about here. Global heating is the physics of what is happening to this planet. This planet is getting hotter. It just is. There's some discussion still about how hot it might get, but the fact that it is getting hotter is irrefutable. And there's no explanation for how it's happening except that humans have polluted the atmosphere with enough greenhouse gases that heat is concentrating in the atmosphere and transferring to, like, say, for example, the ocean. And when we measure the temperature of these things, everything's getting hotter. Climate change, so-called, is a result of global heating. Global heating is the driver. Global heating is the physics. Climate change is what you're going to observe. It's what's going to happen to you. Your climate is likely to change. And so you think, okay, well, if it's global heating, then my climate is going to get hotter. Yes, probably, almost certainly, on average, hotter. It might get extremely hot. It might get it might get a little bit hotter. It depends on a little bit on where you are. The global heating is most notable, most measurable in places where amplification is taking place, where the heat accumulation is actually worse than it is in other places. So we see remarkable changes in temperature at the poles, the Arctic and the Antarctica. You could be forgiven for not knowing that. Of course, no one's there to speak of, so it's not like in the daily news, nightly news. The other place where we get increased heating is in the winters. Believe it or not, you'd be forgiven if that didn't seem like that was happening, but it is happening. The other place where we get global heating, unusual heating, is at higher altitudes, and in particular, like mountaintops above the snow line and things like that. So my wife just walked in. Maybe you'll be able to hear her because I think she's on the phone. So, but these are not places where there's a lot of people. So the heating part isn't always obvious, but it is measurable. We measure it with weather stations. We measure it with ships at sea. We measure it with satellites overhead that measure the entire planet. And it's pretty obvious what's happening. So I just wanted to clear that up. And I'll say global heating a lot, and sometimes I'll say global heating and the resulting climate change, and sometimes just to keep things simple and to go along with the memes, I'll just say climate change. But really, it is global heating, and climate change is the result. Your climate will be changing. It's also worth defining what is climate and what is weather. Climate is what you expect. Weather is what you get. So what this means is that as your climate changes, what you expect in your area, wherever you live, wherever you hang out, wherever you frequent, the climate is what's changing. The weather changes all the time. And the fact that the weather changes all the time will mask the changes in the climate. But the climate, if it's changing, will be reflected in things like the plants that are able to grow, because plants become established and they have a long-term growth pattern. Also, things like the snow line, where is the snow falling at all, and then where does it stick? Um, Snow in areas like glaciers. The glaciers are melting. These are all signatures of climate change that are maybe masked by weather. Of course, eventually your weather does change, and that's really the topic of today. Um, you see weather on a daily basis, and because of your climate, you expect your weather to fall into a bracketed set of behaviors, and the bracket moves from summer to winter and back to summer again. What you expect to have happen, but that is being driven by global heating. Okay, so I just wanted to help you make some sense and maybe give you a framework for comprehending what is coming our way, because it's bad. It's really bad. Okay. And we'll start with the example of weather as we're seeing it recently in the lower 48 states of the United States of America. I'll mention Alaska. I don't know much about Hawaii, but we do hear things coming from Alaska. And I wish I could speak to Europe and the UK and Russia and China, but here in the US, because we're such chauvinists, we don't get much news about what's happening in those places. So I leave it to someone else to point out how these topics impact those places. All right. So what's happening in the lower 48 of the US and including some of the surround. So global heating, just so you know, is heating the Gulf of Mexico, which is water, more than it's heating the land. Water has a very high specific heat, and the oceans are actually absorbing a lot of the heat that starts in the atmosphere. That's where the greenhouse gases are: carbon dioxide, methane, and some others. It's in the atmosphere. So the atmosphere gets hot, but then it transfers that heat to the oceans and other bodies of water, and of course ice, which becomes water when it absorbs heat. The heat is used to do the phase change from solid to liquid. So the heat, quote unquote, disappears into these various places, mostly into the water. But the oceans are getting quite warm. You've no doubt heard about the bleaching events at places like the Great Barrier Reef off Australia, where the water gets so hot that it kind of kills the coral, or at least cripples it. And that's a big deal for them. They're not that they're changing anything about how they do things, but for their tourism and for the fact that it's the largest colonial organism on the planet. It's a big deal if it dies. So they're aware of that, and that's caused by the heating of the oceans. Well, our Gulf of Mexico, which is off of Texas, Louisiana, Mississippi, etc., is getting quite hot. It's sort of a little blind cul-de-sac. There's water that loops up through it and then out around Florida and up the eastern seaboard. But for the most part, it just kind of collects there and it gets hot. And that phenomenon of the Gulf of Mexico getting hot is the result of global heating. A lot of the heat from the atmosphere is going into the water down there. And that's having an impact on weather and sensible heat, meaning heat you can feel or measure with a temperature thermometer. That's having an impact on sensible heat in the states of the South and the Southeast. So here we were in December. They were having record temperatures down there, record 20, 30 degrees above normal for December. Hottest Decembers ever. I've even seen YouTube videos and others where meteorologists, who are by and large climate skeptics, they just don't think this is a thing, nevertheless say that December has been off the charts for these states. At the same time as that is happening, we've been having cold Arctic air masses. Now, words have meaning. Okay, I'm not going to say cold weather. I'm saying something that actually matters. These words have meaning. They are not random words. Arctic air masses. Arctic air masses are descending from the Arctic through Canada and into the northern and western states, and colliding with this hot, moist air intruding into the lower southern and southeast states at a line of collision that goes about from Texas and in a kind of a northeasterly direction up into New England. And so that's where these two air masses are colliding. And the air mass from the Gulf of Mexico is being fed continuously by the hot water in the Gulf of Mexico. The hot water in the Gulf of Mexico is anomalously hot, and it's not going anywhere. It's caused by global heating. And global heating is something that's going to be with us for thousands of years. And it's only going to get worse because we're not doing anything to stop it or slow it down. We're just not. Maybe we will someday, but we're not. And maybe someday we can reverse all these emissions of CO2 into the atmosphere, but right now we're not. And there's plenty of evidence based upon actually the laws of physics that we won't be able to do that. We got energy out of the process of putting those gases into the atmosphere, and we're going to have to expend and spend energy to get those greenhouse gases out of the atmosphere. And where's that energy going to come from? Well, you're going to have to come up with an answer to that, because right now we don't have it, except, of course, fossil fuels, and that really defeats the purpose. So right now, the Gulf of Mexico is hot. It's going to get hotter. It's going to continue to get hotter. It will get hotter, meaning it's going to accelerate for decades, a century, 2 centuries. Who really knows? It's really up to us, but we're making no moves of any kind right now to stop that from happening. So that process of heating of the Gulf of Mexico and the impact that has on the southern states and the southeastern states is going to continue. It's going to get worse, and it's not going to stop, and it's never going to end, and it's never going to go away. That is now a semi-permanent feature of that part of the planet. Hot Decembers, record-breaking Decembers, should become fairly common going forward. Now, the thing about records is, if you break a record for daytime temperature in Austin, Texas on December 25th, Christmas Day, let's say you break a record that day, it makes it a little harder and a little more unlikely that you'll break that record again soon, because it's hard to break records, right? But under global heating, it's not hard to break records at all. It's getting hotter all the time. So actually, in fact, you would expect to break that record sometime in the future. Maybe not the very next year, but certainly some year after that. It's like 2 or 3 years after that, you'll break that record again, because it's getting hotter all the time. Now, a little bit about this Arctic air that's coming down. That's also now a permanent feature. There's a little bit of a story behind that, which people aren't quite as familiar with, because the events that take place above the Arctic Circle, further north than even Canada, don't really register. We understand the Gulf of Mexico, that's where the oil platforms are, and the hurricanes come in, and New Orleans and all these other things, Galveston. We understand the Gulf of Mexico, and it's in the news once in a while, and we talk about the Gulf of Mexico, but we never talk about the Arctic. The Arctic is, some context here, the Arctic is cold. It's freaking cold. It's cold in the summer, it's cold in the winter. Of course, in the winter, it's even colder. Why is it so cold? Well, there's a lot of ice up there. Ice is cold, so that's one start. The ice that's in the Arctic is leftover ice from the last ice age. There was a time when there was no ice up there before the start of the ice ages. What started the ice ages? Well, you could discuss that. I'm sure there's some debate in climatology and geophysics and astrophysics, what started the ice ages. The prevailing theory is that plants which use carbon dioxide in the atmosphere to make their tissues, a process called photosynthesis, plants which dominated this planet at one time and had much better growing conditions than they have now. The plants pulled so much CO2 out of the atmosphere, were so effective at doing that, and burying it in bottoms of the oceans, swamps, bottoms of estuaries, every place. They just buried it. They were so effective at doing that they lowered the level of CO2 in the atmosphere until finally there wasn't enough to keep the atmosphere hot. There you go. And then ice could start to form. And when ice starts to form, it has a reinforcing feedback The ice is reflective, and when it covers ground, which is not reflective, then the ground, which used to absorb solar radiation, now is reflecting solar radiation. Also, the ice prevents the growth of plants, and plants do absorb solar radiation. Of course, that's what they do. And in the process, they create warmth, warm air. And when they're not there because it's too cold, well, then that's also another thing that doesn't happen. So there's this kind of feedback loop where as the CO2 starts to decrease and therefore the planet gets a little cooler, and then there's ice, well, then plants can't grow and they can't pull, they can't reflect, they can't absorb light. And so things get even colder. And eventually, you pull out enough CO2 and there's enough ice forming on the planet as a result of the cooling effect that you can actually get an ice age, and it becomes self-reinforcing. This happened very, very early on, it's thought, in the evolution of Earth as a planet. This planet was essentially a snowball. It became a snowball. You'd have to look that up, how that happened. But we were an icy planet, and it was only because volcanoes emit CO2 that the planet was able to recover from that. So hopefully we won't have that ever happen to us. But I think right now we're going in the opposite direction. We are actually digging up the carbon compounds that were buried in the ground, digging it up in the form of coal, crude oil, and natural gas, as what we call them. And we're combusting those products and releasing them back into the atmosphere. And we're harvesting the energy that was stored, put there by the plants. It's sunlight, stored sunlight. So we're taking that energy out, releasing the waste products of that combustion, CO2, carbon dioxide, and sometimes methane from just how we harvest things. There's a lot of methane involved. We just release it into the atmosphere. So we are reversing a 500 million year process when we do that. 500 million years, 300 million years ago, plants were doing the burying part, sticking it in the ground, and then we come along fairly recently and we're digging it up and combusting it. So we're reversing a terraforming process that the plants did that made this a much cooler planet, less CO2 in the atmosphere, more ice, and then humans came on the scene. And that's been our experience of the planet for the 200 or 400,000 years that we've been around. Not millions, thousands, okay? We haven't been here very long. So as the planet cooled, it got cold in the Arctic and cold in the Antarctic, and ice would form, and that has kept it cold. Well, now we're heating the planet. Well, we're not heating the planet. We are releasing stored carbon that was stored in the ground. We're releasing it into the atmosphere. And the greenhouse effect, in combination with incoming solar radiation, the greenhouse effect is warming the planet. That's irrefutable, and you can argue it if you want to, and whatever. Nobody cares what you think. So the process of having ice, laying down ice, protecting ice, keeping ice from melting, that's all being reversed. And I mentioned earlier that the heating of the planet is actually accelerating at the poles more than it is at the equator. When we say that the temperature of the Earth on average is heating and getting warmer, that's an average of the heating that's taking place in the Arctic, in the Antarctic, and the heating that's taking place at the equator. We average those, okay? The equator is much bigger than the poles, and so it has a little more weight. But in terms of a numeric average, the planet is getting warmer, but it's getting warmer faster and more, to a greater degree at the poles. So why is this important? Well, that's where the ice is. At some point, we're going to start melting ice. I was mentioning that the Arctic is cold. It's very cold, but it's not as cold as it used to be. I would want to look up some data, but the natives up there, the native peoples of the Arctic Circle, are reporting that their lifestyles are threatened. Their lifestyles are threatened. Non-native peoples who live in places like Siberia, who built their homes and their cities and factories on the permafrost, are reporting that the permafrost is melting and their structures are sinking into the permafrost. The roads in parts of Siberia are called ice roads. They don't have to lay down asphalt. They just take a big blade and they just scrape the frozen ground until it's flat, and then they run the trucks on it. And the trucks They don't melt the ice, the ground. They don't melt the ground. They're just rumbling over it. And the ground is so hard that it's just an ice road. You don't need asphalt or concrete. Well, the ice roads are failing. It's becoming increasingly difficult to get around in the Siberian part of Russia. And this story is really common now. You can go to Alaskan villages, the Inuits, the other peoples up there, and they'll tell you that it used to be that the pack ice, which is the ice that floats on the sea, would extend from way out in the sea all the way to the shore. And in fact, when the wind blew, it would pile the pack ice up on the shore. You'd have big, huge piles of ice. But that was really important because it protected the beach and their settlements from the waves of the water. It's all water up there, right? The North Pole is not a place, it's an ocean. So the storms that brew up there in the winter are unbelievable, and they blow the water and the ice piles up on the beaches, but it protects the settlements and the soil from erosion by the gigantic waves by forming essentially a seawall made of ice. It forms a seawall made of ice. Well, that service of the pack ice blowing up onto the beach and protecting the beach from erosion, that service is gone. That was a natural service. They didn't have to build seawalls. They just watched as the pack ice piled up on the beach 6, 8, 10 feet high and provided a seawall. Well, now that doesn't happen anymore. There's still pack ice. It's out there floating around, but it's not solid and there's not very much of it. It's not as thick as it used to be. And the pack ice is going away and it's not providing that service. And their villages up there are falling into the sea. Falling into the sea, they're having to move them inland. They don't even know how far to move them inland. They are people who live on the sea. They use the sea for food and transportation. So they don't want to go too far inland. They don't want to be 10 miles inland. They have to be somewhere, but they don't know really where it's sensible to set up a new village and who's going to even pay for that. The oil companies aren't going to pay for that. Someone's going to have to pay for that. So they're in big trouble. And you go up there, you go up to Alaska and you talk to the Inuits and the other people that live up there, and they'll tell you, oh yeah, this is a big deal for us. Another example of how it's warming up there. The ice is going away. It's getting really warm up there. Now, the Arctic is warming. The Arctic is not as cold as it used to be. I don't know what the actual numbers are, but let's say on an average winter day, it was, 80 degrees below 0 Fahrenheit. And then, now maybe it's 40 degrees below 0 Fahrenheit. That's still massively cold, right? That'll still kill you and it'll be quick about it. But it's important that it's warmer than it used to be. There is a wind called the jet stream that goes around and around and around. Well, there's several of them, but the one I'm talking about here is the one near the pole, near the Arctic Circle. It goes around and around the Earth like this. We didn't even know it was up there until we started flying jets over the pole of the Earth. The quickest route from, say, San Francisco to Japan is not really to go, or I should really say Europe, is not to go across the Atlantic Ocean. Okay, the shortest route might actually be to fly north, to fly over the pole or part of the pole, part of the Arctic Circle, and go to Europe that way. That's the actual shortest line. And when these jets were flying that route at that altitude, they began noticing these really amazing winds. And if you're going one direction from west to east, you got a really heavy tailwind. And if you're going the other way from east to west, you had a headwind. And it made a big difference in how you calculated your flights. So the jet stream became a thing. And that also got scientists looking at atmospheric phenomena and what is happening in the Arctic. Now, the jet stream, as it blows around in a circle, around and around and around the North Pole, and there's another one in the south, and there's another one at the equator and some other things. But I'm talking about the one around the Arctic Circle. As it blows around and around and around, it captures cold air up there, captures it. It's also called the Arctic ring fence. It's a ring fence. It's a circular fence. You can't see it. It's defined with an air, like an air fence that goes around It traps the cold air up there. The cold air can't get away. About 10 years ago, atmospheric scientists began noticing that there were loops forming in that jet stream. It was straight, mostly for a long time, all the time we've been studying. It was just a straight ring around the North Pole. It began to loop down, Loop would come down, it would come down, and then it would go back up. It was like, what is that? Why is it doing that? That's weird. And that's cold air, right? That's Arctic air, way, way below zero. And that's not weather. That is not weather. That's an air mass that broke free of the Arctic Circle and dropped down and then went back up. These are moving air masses. That's Arctic air. It's not supposed to be below the Arctic Circle. There's a ring fence that keeps it up there. And they began noticing that something was happening. A woman named, I think her name was Jennifer Francis, not a climatologist, not an atmospheric physicist. I think actually just a statistician. She was a statistician. And she began looking at the data, wondering, so what statistically is going on with this? And she came up with a theory that was roundly derided at the time. And even at the time when the people were saying, that's the dumbest thing I've ever heard, I thought, no, she's hit on something. You better look at this. And a few years later, they was like, yeah, she's right. And what she discovered was the jet stream was slowing down. It was still moving. It was still there. The phenomena between the cold Arctic air in the north and the warmer air at temperate levels and the rotation of the Earth, all those things combined, was still creating this jet stream that was going around and around and around. It's really an emergent property of the planet itself. The planet has a jet stream because of how the temperature differences between the north and the south, well, the equator, the north and the equator, and the rotation of the Earth. All these things combine to give us a jet stream.
Jennifer Francis is a PhD.
Yes, I know.
Yeah, and
she's a statistician, a mathematician.
In Arctic weather and climate, so it's specific.
Yeah, well, she is now, but at the time she was kind of not. I may be telling this story wrong. My wife is on Google looking her up. But she kind of came out of left field, okay? And she was the one who said, guys, you may have a problem here.
She studies the Arctic.
Yeah, there may be a problem here. And so she alerted people to what she thought was going on, which is that the jet stream was slowing down. And now that's accepted fact. The jet stream is slowing down. Why is the jet stream slowing down? Well, the jet stream is created by the temperature differential between the North Pole and the temperate latitudes, so about where we are right here in California. That temperature difference, when it's great, it creates stronger winds than when it's less. And so what's happening? And I'll get to why that makes loops in a moment. But as the Arctic warms faster than the temperate latitudes, the differential between that extreme and the other extreme starts to decrease. And as the differential between the two extremes decreases, the winds also decrease. Now, the Earth's rotation is still a constant, so the jet stream is still going around basically from west to east, but its amplitude, its speed, its actual speed over the ground has been slowing. Now, when a laminar flow, like let's say a river, when a laminar flow loses energy, it stops flowing in quite so straight a line, and it begins to what we call meander. Okay, as it loses energy, other types of dynamics take effect, things like turbulence and random features and things like that cause it to meander. And you'll see that in your mountains, on your gradients, your creeks move faster and in a straighter line than that same water a few miles later when it hits the flats. It slows down and it starts to meander. It drops its sediments, and the sediments build up in banks, and then the river starts to meander. You get oxbows and all kinds of things. So what she demonstrated statistically was that the jet stream was slowing down, and as it slowed down, it began to meander. And as it began to meander, it was creating loops, just like a river does in a river valley, creating loops. Now, these are not permanent features. They break loose, they form a loop, and then the loop pinches off and it closes back up again. But in the process of looping down, it pulls behind it cold air. Now, meteorologists call these lower hanging loops troughs. They're generally lower pressure. Well, they're always lower pressure. They have a certain rotation and some other things. But for our purposes here, the fact that a line at the equator, at the Arctic Circle, forms a loop and drops down, the cold air enters that trough and comes down with it. Okay, as it drops down, forming a loop, the cold air comes down with it into that trough. And so we began seeing these events where cold Arctic air, as an air mass, not cold weather. Yeah, you'll get cold weather from it, but the mechanism is an Arctic air mass that has escaped from the Arctic and is dropping down with this meander. And they began coming down far enough to be detected, meaning we have weather stations and people living in cities in inhabited parts of the world. So Europe, the UK, parts of Russia, China, and of course the United States. And the same thing is happening in the South, okay, in the Southern Hemisphere, but that's not really our topic today because nobody lives down there. Sorry, Australia. Nobody really lives down there. Nobody really cares. It's mostly ocean. There's some air masses, and there's Australia. So most of the drama here is in the Northern Hemisphere where this is happening. So now we have this phenomenon, which we're actually seeing in December, where you can have record hot temperatures caused by one aspect of global heating, which is the heating of the Gulf of Mexico. That's one thing. That's a thing. That's a real thing. It's really hot, and it really heats the air, puts a lot of moisture in the air, and that moisture, that hot, moist air makes its way into the southern states and into the southeast and sometimes even into the northeast. Record hot temperatures in December, off the charts, completely insane. While that's going on, you can have a meander from the Arctic, where the ring fence is beginning to break down, and that cold Arctic air, which, remember, isn't even as cold as it used to be. Arctic amplification is a real thing. It's getting warm up there faster than it's getting warm at temperate levels. Although it's getting warm everywhere, it's amplified up there. That Arctic air, which isn't even as cold as it used to be, drops down behind these meanders from the slowing jet stream, and it just freezes everything. That's one of the things that happened to Texas last year, was when that cold wave came down and just froze everything, including the natural gas pipelines. That was one of those events. And right now they're happening pretty regularly in December and I guess into January. Now that doesn't mean this will happen every year, but the conditions that allow for this or incent this to happen are permanent features of now the planetary physics. The heat in the Gulf of Mexico is a essentially permanent feature of this planet. That is not going to change. It will just get worse, and it will get worse for 100 years. And who knows when it will ever get better? It may never get better. It may get hot to a point, maybe the heating levels out, but it will never cool. It will always be what it is now, except that it gets worse. And these meanders from the Arctic, because the changes in the Arctic are now a permanent feature, except that they may get worse, okay? And almost certainly will. They are a permanent feature, except that they will get worse, okay? That situation doesn't change. And there's something that exacerbates that situation. This Earth is on an excursion. It is trying to balance the books with all this heating. And when that cold air mass drops down from the Arctic and descends into the western and central states, unknown to you, because you don't live up there, there's another air mass somewhere else nearby that's going up to replace it. It's going up. And so you end up with the situation where the Midwest, you can have this freezing air mass that came out of nowhere, where it was record temperatures. In I don't know, Arkansas, record temperatures one day, and then 2 days later, or even 8 hours later, it's freezing or below zero. It can be below zero. Okay. 8 hours later, that's not weather anymore. That's not weather. That's atmospheric physics. It's not weather. Weather is, well, some clouds came in, it got colder, maybe it snowed, and it was cold for a while after the snow, and that's weather. Okay. This is not weather. You're not seeing changes in the weather. If you're watching these things happen, these are changes in the Earth's dynamic climate system. And there's nothing you have experienced in your entire life that has prepared you for this. Nothing. This is off the charts. This is operating outside of weather. This is not weather. Yes, you'll have some weather. It'll snow. The weather forecast for today is snow. And the weather forecast for tomorrow is record heat. But it's not weather. I know the weather forecaster will tell you, I have a forecast for you. Here's the weather forecast. But it's not weather. It isn't. It's a breakdown in how the physics of this planet operate. This planet is on an excursion. The major masses of air on this planet are moving. They're moving. And these movements are driven by heat. And when that cold air mass drops down from the Arctic at 120 miles an hour, it's on the move. It's moving across the planet at a tremendous rate. When it drops down somewhere else, there's another air mass that's rising up in latitude towards the North Pole to replace it. Now, that doesn't make its way into the weather report. Maybe if you live in Alaska or Siberia or Scandinavian countries, then your weather report is like, where's all this heat coming from? Well, that's because a huge air mass left the North Pole to come south, and another huge air mass, or more than one, several, has to ascend back to the North Pole to replace it. And this is the process by which Arctic amplification takes place. This is the process by which we lose all of our ice in the north. This is the process by which the North Pole warms and becomes more temperate. This is the process by which the entire planet finds a new equilibrium. All the hot air is going to the poles. The cold polar air is getting warmer all the time, and then it descends, it leaves, and it goes to the south, where, of course, it becomes warm air again. And so this constant churning is like boiling water in a pot. The heat is one place, and it's just stirring throughout. And our planet's atmosphere is being stirred by global heating. What you're going to see is changes in your climate, and you're going to see weather patterns that are simply off the charts. This is not normal. This is not weather. This is not weather. This is climate disruption. We are seeing things happen on this planet that have never happened before, because the physics were not possible before humans started digging up fossil fuels and burning them and releasing the CO2 into the atmosphere. We have massively screwed things up. Now, this planet and its planetary physics will go wherever it needs to go with all that excess energy from the heat. It will do something with that heat. It will use that heat to do work. It will melt ice. It will heat water. It'll heat the oceans. It will dry out the landscapes. It will dry out the forests, or it will create rain, and it'll create new forests where there used to be deserts. We don't even know. But none of this is weather, and none of it. It's all climactic chaos. I've said before in other videos, in 10, 20 years, you're not going to recognize this place. You're not going to recognize any part of this planet. Everything is going to be completely plowed up. The landscapes, the weather patterns, the climactic patterns, the places of the habitable zones, it's just going to be completely blended. It's going to be through the whole thing in a Cuisinart. And it starts early days with exactly what we're seeing right now. Massive heat coming up from the oceans. Massive cold dropping down from the Arctic. Arctic air masses, not weather. Not, oh, it's winter. We always have snow. Not like that. Arctic air, okay, dropping down and causing disruptions. Now, all the time those masses are dropping down, there's another masses going up there to warm things up. So watch what happens. Watch what happens. This doesn't last for very long. Now, I don't actually know how long we're going to have this type of blender Cuisinart effect. This could go on for 100 years. But however long it goes on, watch what happens. Watch what happens. Now pay attention here. As the poles, both poles and Greenland, start to warm, the jet stream starts to fail and finally just becomes nothing in particular. Yeah, there'll probably always be a circular motion, just like there's a circular motion at the equator. There's a gentle circular motion at the equator that creates in the Atlantic basin what are called the trade winds that the sailing ships used to use, right? It's just a gentle motion, circular motion caused by the prevailing winds and then the orbit of the Earth causing things to bend and whatnot. So there will always be a wind up there, but it's going to decrease. The other thing that's going to happen is it's just going to get warmer up there. Exchanging air masses, the cold comes down and the warm goes up. You just keep doing that. Eventually you melt all the ice, trees and plants grow and it just gets warmer and it just stays warm. The pack ice all melts, all of it, it's gone. At least most of the year it's gone. There's no ice at the pole. There may be ice left on Greenland. In fact, they refer to, at some point, Greenland is going to become the North Pole in terms of cold, right? Greenland is already called the third pole. It's so big and there's so much ice that it's like the third pole. You've got the North Pole, the South Pole, and then there's this big chunk of ice on Greenland that's like a third pole. Well, Greenland will become the equivalent of what we now call the North Pole. It'll be the coldest place in the northern hemisphere, which is going to completely screw up weather patterns. Right now, our prevailing weather is based upon the cold is in the north and the heat is at the equator, and there's this bunch of exchange that goes on, and there's a bending of that exchange because of the Coriolis effect, the Earth's rotation, and that's weather. That's where you get your weather. That's where you get your climate. Well, when Greenland is now the new pole because there's no cold anymore up north, it's all over here on Greenland. Well, that completely changes everything. We don't even know what the weather patterns are going to be like. I don't even think anyone's looking at that, running those models. That would be, it's going to go completely off the charts. Who knows what that's going to do? Gradually, as the North Pole and the South, but I'm talking about the North Pole here, as it warms, then these Arctic air masses that drop down will also be warmer. If it's normally 80 degrees below zero, and then it's 40 degrees below zero, and then it's 10 degrees below zero, then after a while, it's not even freezing anymore. And we're done. We don't have ice at the poles. We don't have a cold North Pole. And we are very gradually over time through these exchanges of these huge air masses, cold for warm and warm for cold, as we do these north-south exchanges here in the Northern Hemisphere, the world's temperature starts to equalize. And pretty soon there is no cold up there. Pretty soon there is no ring fence and there is no Arctic air masses, and that whole thing stops. That whole thing stops. There won't be any more air masses dropping down, or if they do, they're really not that much colder than the air they're replacing. Now, I don't know how long that's going to take. That could take 100 years, but that's the direction all this is headed, because the features that are going to drive this change are present now, and they are essentially permanent. This planet is going to keep warming. The Arctic is going to warm more than the equator. The air masses are going to keep exchanging north to south here in the Northern Hemisphere, and the Arctic is just going to get warm, and all the ice is going to melt. All the reflective surfaces are going to be gone. It'll be absorbing heat directly from the sun. It'll be colder in the winter because the days are short and the nights are long than it is in the summer, where the days are long and the nights are short. But apart from orbital dynamics, it'll be much warmer than it is now. And probably at some point, you could live up there in shirt sleeves most of the time, just like it is in, Seattle, Portland, right? Seattle and Portland, lots of warm days, sun is out, not a problem. So that's where all this is headed. That's how the world becomes hot. And the other thing that's happening is that a lot of the places on this planet that are heating up because of global heating are cooled by some of these air masses. Well, when that's a natural service, call it natural air conditioning. The heat that's being accumulated by this planet has a place to go where it can do work. It goes to the north, or of course, in equal amount to the south, and it finds ice and it melts it. Well, when that ice is gone, and when the permafrost is gone, and the only ice left is on Greenland, then the amount of cooling you get from that service diminishes and might even disappear. So these air masses that right now are rising up to go to the North Pole and be lost to space and melt ice, those air masses will just go up there and it'll just be hot. And the air masses that come down won't be that cool. And the planet starts to warm. And this process of the heat right now is doing work. It's warming the oceans and it's melting the ice. That process stops, at least as far as the ice is concerned. The ice there isn't any. There's no place for the heat to go. So it doesn't go anywhere. At that point, the heating of the planet could become a runaway effect. You haven't seen much heating from global heating, in the last 100, 300 years, but this has really been an important process. You haven't seen much actual heating. Well, don't kid yourself. That doesn't have to be a feature of the future. When the ice is largely melted, and we're not getting cold air masses coming down to cool us off, and the heat goes up there, and it just the ice is all melted, and the heat doesn't go away doing work like that, then the heating on the planet as a whole could really accelerate, really take off. Now, I think that there's an interesting story about where that goes. And this is some speculation. Everything I've just said is not speculation. It's atmospheric physics. All right? Simple as that. Heat has to go somewhere, has to do work. The breakdown of the ring Arctic fence is well understood. The meanders of the jet stream are well understood. The heating in the Gulf of Mexico is easily demonstrated. These are all permanent features now of the Earth dynamic system. Where it goes is not a permanent feature. That's our future, right? We are on an excursion. The planetary system as a whole, as defined by parameters like temperature and humidity, that system is now on the move. We kind of don't know where it's going to go, but we do. We do know. We do know. Before the plants were done pulling all the CO2 out of the atmosphere that they could and burying it in the ground, this was a hot planet. It was green from the equator to the poles. Antarctica, which is a continent, has fossil forests and the bones of reptiles and amphibians. Okay, so that ground wasn't always where it is now because of continental drift. It drifted down there with some of those features intact, but nevertheless, even when it was on its way down to be in the South Pole, it was still warm enough down there to have crocodiles at the poles. So that's where we're going to head. That's where we're really headed. And all the heat that gets absorbed by the oceans and larger bodies of water, fresh water, contributes to atmospheric moisture. When the waters are hot, they evaporate water into the air, and that moisture comes down somewhere. It can come down either as rain or sleet or hail or snow, but as the atmosphere warms, it's going to tend towards the rainy side. And there's more moisture in the air because the oceans and water bodies are so hot. And it's going to come down preferably, it's going to be more likely to come down as rain because of the general heating of the entire planet, making ice impossible, including snow and hail, right? Well, you'll probably always have hail. Hail is a feature of convection, and you throw water high enough up into the upper atmosphere, you could find cold conditions near the near the top of the atmosphere where you can form hail. So we'll always have hail, but we may not have snow. And even if we do, it may melt before it hits the ground. And even if it hits the ground, it may not stick. So the future scenario for all of this in a heating planet with less cold in general, including at the top of the atmosphere, is that we tend to statistically see less water in solid form, ice, and more water in liquid form, and more of that. There's more moisture in the air, and it's probably going to come down as rain. So statistically, okay, on average, it's more often going to be rain than snow because of the heat, right? You can't have snow without heat. You can't have snow when you have heat. I got to say that differently. So we can expect to see over time, as the Earth system migrates from this temperate system more into a tropical Earth system overall, in totality, more rain in more places. So the irony could be that even though the planet system is getting hotter, global heating, the direction the climate will change may not be towards what you associate with heat, meaning deserts. Yes, there could be desertification, and initially that might happen in a lot of places. For example, they're thinking that parts of the Amazon rainforest may become dry and temporarily turn into savanna. But I think it's only temporary, because ultimately, with so much hot water surrounding continents and so much evaporation and so little cold to freeze that evaporation into snow at high altitudes where it can be stored, we're going to get rain, a lot of rain in a lot of places. It's going to come down. It's going to be biblical. And, I don't want to say that's what's happening right now, but right now, today, 2022, early January 2022, certainly December 2021, we saw massive amounts of rainfall in the Pacific Northwest. Now, we're also having a La Nina event. The La Nina is half of the ENSO, the El Nino Southern Oscillation. The other half, the other binary, is El Nino. La Nina and El Nino are different states, different binary states of the ENSO. So as the ENSO flips back and forth between those two states, La Nina, which we're having right now, tends to direct an atmospheric river into the Pacific Northwest. And El Nino tends to direct that same atmospheric river into the lower western states. And California, for example, will tend to be drier during an La Nina swing and wetter during an El Nino swing, and about normal in the transition between the two binaries. So we are currently in a La Nina phase, and sure enough, atmospheric rivers are pounding the Pacific Northwest. But the amount of moisture in the air to do that, the amount of moisture in the air to rain down during a La Nina event, is increased by the increase in temperature of the water. There's more evaporation, therefore there's more precipitation someplace else. So even though the atmospheric rivers might be determined by the La Nina phase, and the fact that it's raining somewhere and not somewhere else may be due to La Nina conditions, the amount of water in the atmosphere we should expect to be increased over what it would have been otherwise, because of the warm waters in the Pacific and elsewhere, Gulf of Mexico and other places, releasing more atmosphere and more moisture into the atmosphere. So these are all changes in climate. La Nina and El Nino will be with us for a while. They may stop at some point. The conditions that gave rise to the ENSO oscillation may not continue, and we may lose the ENSO, just as we're kind of on the threshold of losing the AMOC, which is a water circulation pattern off the eastern U.S. associated with the Atlantic Ocean and the hot water that spills out of the Gulf of Mexico and goes up the East Coast and then into the North Atlantic, warming in its passage the Scandinavian countries and what we call the UK. The AMOC, that current, that Gulf Stream, as people call it on the East Coast, the Gulf Stream, the AMOC is slowing because of changes in the conditions of surface waters in the Atlantic. What effect will that have on things? Don't know. Could get colder in the UK as a result. Could get colder in the Scandinavian countries and Northern Europe as a result. That's one expectation. That was actually the premise of the movie Day After Tomorrow. They went further with it, which is, give them some dramatic license. But the science they were at least discussing, a shutdown in the AMOC could lead to cold conditions in places that used to be warmed by the Atlantic circulation. Well, they get colder. That science is pretty well accepted. Now, no one's willing to go out on a limb and say when the AMOC is going to shut down and completely or significantly, and no one's willing to go out on a limb and say when the ENSO in the Pacific, the El Nino Southern Oscillation, will also shut down or no longer become a feature. But given the changes we're seeing in the hydrosphere portion of the Earth dynamic system, given those changes, we can expect changes in the AMOC and in the ENSO and in as the circulation patterns shut down, we're going to have big problems. I mean, serious changes. Let's call it that. Whether they're problematic or not, I guess we'll find out, won't we? Another thing that's driven by heat accumulation in water are hurricanes, and in the Pacific Basin, typhoons. Same phenomenon, different name. Don't expect more of them because it's kind of a chaotic nature of how they are formed, but we expect them to be stronger because the heat contained in the water is what spins them. It's complicated. I don't even completely fully understand it myself, but they'll tell you that when a hurricane passes over warm water, for example, in the Gulf or the South Atlantic or wherever it happens to do, that Caribbean Sea, when a hurricane passes over warm water, it will increase in intensity, and it can do it very quickly. They've even had to invent a term called bombogenesis to talk about how these bomb cyclones can rapidly intensify. The intensification comes in the form of spinning faster, getting physically larger, ascending higher into the atmosphere, containing more rain, those kinds of things. And that's kind of what happened to Hurricane Katrina. Hurricane Katrina had entered the Gulf of Mexico at as like a category 1 or maybe 2, and then it passed over a warm loop in the Gulf of Mexico and rapidly intensified to in size and wind speed to something that was absolutely off the charts. And that's going to be happening more often. That observation, wow, that was off the charts. Okay. That observation from your friendly neighborhood meteorologist, record this, record that, off the charts, don't know what's going on. That observation is being driven by global heating. Heat is the common ingredient to all these observations. Global heating is driving the record temperature in the Gulf of Mexico. Global heating, therefore, indirectly, is driving the record temperatures seen in the South and the Southeast U.S. During December. Global heating is causing the Arctic air to warm faster than the other air, and there's now an imbalance in energy. Therefore, that's slowing down the jet stream. Therefore, global heating is causing these loops, meanders to form in the jet stream, which are bringing down cold air from the Arctic. Now, that air is not as cold as it might otherwise be because the Arctic is warming, but it's cold enough to kill you, okay? And it's not supposed to be down here. It's not supposed to be here. It's supposed to be up there. Well, now it can break through and come down here, all right? So all of this stuff is driven by global heating, including the cold temperatures. That's driven by global heating. I know that's not intuitive. Well, you're just going to have to stop thinking of all of this as weather. Because it's not. This is Earth physics. This is Earth dynamic system. The entire planetary system is on the move. That's not weather. That is not weather. And just because your weather drone gets on the TV every night and talks about the weather, that doesn't mean it's weather. It's climate change driven by global heating. And it's not going to stop. It's probably not ever going to stop. And we're not even certain that we're going to survive it. Not as a species, certainly not as a civilization. There's nothing to guarantee that we can turn the corner on this and emerge in a good place. We don't know where this thing is taking us. We're on this planet and it's going somewhere, at least in terms of its physics. It's going somewhere and it's taking us with this, and we have no idea where. Except I think it's going to be a lot more rainfall everywhere. And then, of course, sea level rise, because we're also melting ice everywhere. We're going to have sea level rise, more water where you don't want it. We're going to have more rain, more water where you don't want it. We're going to, rain is great, right? Need more rain, more crops, more, fill the reservoirs for summer skiing and blah, blah, droughts go away, plenty of water to drink, lots of water for the garden. But a lot of our crops don't do well in the rain. Period. That's all there is to it. A lot of our crops and our animals, the way we raise our animals, don't do well in the rain. Ask your Midwest farmers, how do you feel about rain? Well, it has to come at the right time. It has to be the right amount. So for, the 400 years we've been growing grains in places like Russia and Europe and the U.S. Midwest, it was always just right. It was always this is a Goldilocks thing. And sometimes, it'd be a little too much rain and sometimes not quite enough or not quite at the right time. And there'd be a problem with the crops. But overall, the climate was stable. We understood it and we could make predictions, and we planted wheat this time of year. We harvested wheat that time of the year. And that just worked out fine. Well enough to feed 8 billion people, right? We went from almost nobody on this planet, 300 million people, to 8 billion people, because all of that was predictable within bounds. And even if it wasn't working in the US Midwest, well, it was working in Australia, or it was working in Russia, or it was working in India. And so there was always food for 8 billion people currently. Well, now we don't know that. Go talk to your Midwest farmer and ask them, so what happens if it rains 4 times as much as it used to? What happens? Well, I think we'd have to plant some other type of crop. I might have to go to peanuts. I might have to, I might put orchards in, have nut trees or something like that isn't quite so sensitive to the rain. Okay. Well, that's a big change, folks. That's a big change. Are you ready for that? Are you ready for that? I don't think you're ready for that. You're not ready for that. You're not ready for that. You're not ready for crop failures. And the problem with the crop failure is, for many, many years, decades, farmers will, because they don't know any other way, and no one's giving them any guidance, right? Farmers will, every year, fire up the John Deere and go get the seed and go get the fertilizer and, plow that field and plant those rows and do all this stuff and lose their crop. They won't know what else to do. They're just, back to planting. It's planting season. Fire up the John Deere, go out and plow the fields. Well, it's too wet. Can't plow the fields. Okay, I plowed the field and it's still too wet. I can't put the seeds in. Well, I put the seeds in and it's still too wet and they're not coming up. And now it rained on the baby seeds and everything's drowned. It's like, well, that didn't work. But I bought crop insurance, so I guess I'm indemnified against losses and I'm fine. But, there's no food. The farmer's okay. He did what he does. I'm a farmer. I do what I do. And if it doesn't work, I get paid anyway. And the farmers are okay. So they have no real incentive to change how they do things. And what would they change to? There's no guidance. They don't even know what to do. And maybe there are varieties of wheat that do better with a little bit of rain. And maybe there's varieties of corn that do better with some rain. And who really knows, right? Maybe they can figure that out. Maybe they can genetically engineer their wheat, or they can go and they can plant rice, right? Rice does really well in the flooded plains. So we'll plant rice this year. We'll plant rice for the rest of eternity because it's raining all the time. And then you start fighting the trees. You start fighting the trees because trees do really well with a lot of rain and with warmer conditions. So pretty soon you have trees everywhere. Nothing wrong with trees. We like our trees. But then the trees start growing in your fields and you're out there with chainsaws and whatnot, killing the trees, and spraying the trees with pesticides and pulling their roots out and burning the trees. And it's just this constant fight to keep the trees from taking over because they're doing really well. And your wheat crops, not so much. And maybe there's entire wheat fields that you just abandon. It's just too low. This is low parts of my field. It gets flooded easily. It's wet most of the year because the rivers and the creeks keep rising and they keep flooding this lower area. I'm going to give that up. Okay, well, 5 years later, it's full of trees because trees don't mind that at all. And now that's land you're not ever going to till again. And we start to lose that battle, right? The system, the earth dynamic system is on the move. It's going that away. All right. And that away is unfamiliar. We're off the map. Okay. Over there. Yeah, I don't know what that's going to mean. But that's where we're going. We're going there. And we don't know what's going to mean. And that's when it starts to bite. When it's not really weather anymore. And the weatherman comes on this, says, well, it's going to be cold. Well, it's going to be record heat. Well, now we're back to freezing cold again. That phenomenon of acting like it's normal isn't going to fly. That's what we're doing. We're doing that right now. We're not having the discussion that I just laid out in 1 hour and 5 minutes. It's complicated. It's difficult. It's painful. It's fraught. There are some uncertainties, but there's not as much as uncertainty as you think. There's not nearly as much uncertainty here as people would like to believe and hope. Like, well, maybe next year will be better. There's no uncertainty with regards to that. No, it's not going to be better. All it gets is hotter. It gets hotter for a long time. It gets hotter. Even if we stopped burning fossil fuels today, it would continue to get hotter for 10 to 20 years. Then that's assuming that the changes we made in the Earth system don't simply make things hotter on their own. If we're not careful and we allow the heat that we're pumping into the system to melt too much ice, then there's not enough ice to keep this planet cold. And it just starts heating on its own. And it becomes what we call an aggravating feedback loop. The melting of the ice allows things to get hotter. The extra heat melts more ice. And pretty soon, the ice cap on Greenland has flowed into the sea, and you've got 70 feet of sea level rise. Or the Thwaites Glacier, so-called Doomsday Glacier, aptly named, has slid into the ocean, and you've got 20 inches of sea level rise. And then they have the other of 24 doomsday scenarios, all trigger because the system got too hot to have ice. So the ice goes. And now you've got 24 doomsday scenarios, all knocking on your door at the same time. Plus, all the extra atmospheric moisture causes rain in places where it shouldn't be raining. And for 300, 400, 500 years, frankly, 8,000 years, we expect things to be a certain way. That's called climate. It's what you expect. Well, climate change is change, and that's going away. It's going over there now. Your climate Venn diagram, the things you can do, are over there somewhere. And you're going there, whether you like it or not, whether I like it or not, whether we like it or not, or approve of that message, that's where we're going. And physics is taking us there. Physics, not politics, not conservatism or progressivism or alt-right ideology. That's not what's taking us over there. Planetary physics is taking us over there. And you, my dear, are on that train. Who was it that said it? My wife will know. We are not passengers on this ship. We're crew. It supposedly it's up to us. But at some point, do you remember who said that? Was that Jim Bendel? Oh, yeah. The science guy said that in an interview we just saw like recently, having a senior moment. The science guy, okay, Bill Nye, the science guy, said that we are not passengers on this ship. We are crew. Now, what he was trying to say is it's up to us on where this ship goes. That's a cute thing to say.
Crewmates, right.
It's a cute thing to say. It puts responsibility on us to steer this ship and make sure this ship goes where it needs to go and blah, blah, blah. And it's cute. And I laughed. I thought it was cool. And maybe it's still true that we are the crew on this ship. Maybe it's still true. But I can tell you something. Very soon now. Very soon. In fact, maybe even it's already in the rearview mirror. We are not crew, and we are not steering this ship. We steered it and we sent it on a direction, and so that's where it's going. But at some point, we do become passengers. At some point, we can't turn this thing. We're just going along for the ride. At some point, we may already be there. I can't even rule that out right now. I still hear people say, well, we can turn this around. We can reduce or curtail our consumption of fossil fuels. We can find other ways to save the day. And maybe we can turn this around and steer this thing and have some influence on this system. And I'm at the point where I'm like, I don't think so. Now, to some extent, that's a guess. That's a scientist saying, looking at the data, not real happy with what I'm seeing here. And you say we can still turn this around? Maybe not. Something steered this thing, whatever that really means, 40 years ago. But now, not so sure. YouTube is telling me that my connection is unstable. We have bad internet, but I sometimes wonder. Because I'm saying some really scary things here, right? All of a sudden my connection is unstable. Really? Anyway, that's about all I have to say. Trying to make some sense of the weather, as they are calling it, and trying to put some context on that, and trying to convince you, whoever ever gets around to listening to this, that I think we're in trouble. I think we're in trouble. I think it's broken. I don't think we can repair this. Doesn't look good. Magic 8 Ball says maybe not. Right? Magic 8 Ball says not a good time. Too late. So I guess that's all I really wanted to say. There's a lot of information packed in there. If it doesn't make sense or it doesn't gel with you, I suggest you go back and listen to this more than once. My other videos, I talk about some of this stuff, not quite as explicitly on this particular problem of air masses and the place where all this is going. But I think in the future, because I don't really care about climate science anymore. There's plenty of people who will read science articles to you and read about the Doomsday Glacier and read to you about what's happening with the animals in the Arctic, and I just don't care anymore. But I do care about evidence that this thing has spun out of our control. Right? This idea, according to Bill Nye, that we're not passengers on this ship, we're crewmates, and that we have our hands on the wheel and we have our hands on the engine and we can turn this ship around. And that's an interesting thought that I fear is actually not correct. I don't think that's correct anymore. I think we are being taken for a ride. So I'll leave you with that until I decide I have more to say on the topic, and then I'll be back. Bye-bye.